Okay, so we're going to run the simulation for vMinteq. I have the instruction for running vMinteq up here, and this is the vMinteq program that is going to help us study chemical precipitation of copper in the presence of NTA, and how adding calcium changes copper precipitation, and also how EDTA influences precipitation of copper. So the first thing I want you to do is go to this web link and download and install the vMinteq program. This is a Windows only program, so it does not run on Mac. Those of you who have MacBook, we have about 20 computers in Germano Lab. That's in the first floor of this building, Patrick Taylor Hall. You may want to go there and get this part done. But let's get started with this one. I'm going to follow the instruction I posted on Moodle and walk you through the simulation now. So the first step is the ionic strength to 0.1 molar. So ionic strength fixed at 0.1 molar. Add components right here. Select Na plus sodium. So go to this drop-down menu, type in N. It will bring out the list of components with N. Select Na plus, and we're going to add 0.1. Remember, it's all molar concentration, moles per liter. Add to list, and then add nitrate, NO3 minus, same concentration, add to list, and then add Cu2 plus, which is copper. So plus C, and it brings up Cu2 plus. I want to add 0.001 molar, add to list, and at this point we're not going to add NTA. To view the chemicals we added, just click here, it will bring up with all the chemicals we added. So back to main menu, solid phases and excluded species. So click right here, select specify possible solids, select this option, go to the drop-down menu, select copper hydroxide. What we are saying is when copper precipitates, we are saying only copper hydroxide is formed. That's our simulation setup. Click Add, back to main menu, multi-problem suite right here. Click on this, suite 1 parameter, select this. I want to do 41 simulation. I want to sweep pH with starting value of 3 and increments of 0.25. With starting value of 3, increments of 0.25, if the model runs it 41 times, it will go from 3 all the way to pH of 13. So we did this part. Now choose components right here. Choose components. Go to the drop-down menu, copper Cu2 plus, total dissolved, and add. Save this one. This is our simulation setup. We're going to save and back, and click Run vMinteq. In this one, select the sweep results. Select on this one. Now, this is the result of our simulation. Start with pH of 3, 0.25 increments, total dissolved copper concentration. It goes all the way to 13. Now click on Print to Excel, and it brings up an Excel file with your numbers. Now this is in molar concentration. So I'm going to change this to M, and this is total dissolved Cu2 plus moles per liter. I wanted milligrams per liter. So equal to this one times 63 is the molecular weight, 63 gram per mole, and we want to convert to milligrams per liter. So 63 times 1000, that will be 63,000, and that is the initial concentration. For the amount of CO2 plus we added, the initial concentration is about 63 milligrams per liter. Now get this cross sign, double click, it will fill the formula for all the cells. So into Excel, we multiplied by 63,000. Now we want to plot pH in x-axis, dissolved copper in y-axis. Let's make a new worksheet and rename this as plot. Now I'm going to copy the pH first, copy this one and paste it here. Go back, copy the concentration in milligrams per liter, and let's do this one. Go here, paste special, paste as link. Essentially, it pastes as a link, meaning any change you do will automatically get updated here. So I want to move this one row higher. Okay, and this is no NTA. We did not add NTA at this point. And let's make the plot now. Plot pH in x-axis, dissolved concentration of copper in y-axis. So insert, go to this one. I prefer this. Right click, select data, add, no NTA. We want pH in the x-axis and dissolved copper in y-axis. Okay, so this is our plot. Click OK, and I want to do some formatting. So I don't want this title. I'm going to delete this line, delete the horizontal line. Let me make this bigger. Double click, border. I want a solid border with black line. Same way here, I want black line, and this one too, I want black line. So each time when I double click, it automatically changes here. Okay, so everything is black line. I want to do one more thing. Double click here, it brings the axis option. I want to add tick marks, major tick mark, outside, minor, outside. You see those lines showing up here. Same way for x-axis, outside, outside. And now I'm going to click on the edge, double click, border, no line. So I don't have an outer line. I want the inner box, all black lines, and select this one, go to font, change the font size to 12, font type to, I prefer Times New Roman, but you are free to use whatever works for you. So this is our graph now. Let's add the double click. Let's add the axis title, primary, which is pH, and axis title, vertical is total dissolved copper, in milligrams per liter. Okay, and I'm going to click again at the corner, go to home, make all the fonts black. It was an ash color, now it changed to black. Okay, so we ran the first simulation. We added sodium, nitrate, copper. Now we are going to do the second one. Before that, let me save this one. and I'm going to save this in desktop. Chemical precipitation. Let's make it smaller. Now, so we finish up to step number 12. Number 13, close this one, back to input menu. So back to input menu, check show organic compounds right here. Check on this one. Now click this drop down menu, type in N, it will show you up NTA. Where is NTA? Right here. And NTA we want to add for a concentration of 0.0001. Add to list. So we finished step 17. Step 18, run vMinteq. And follow step 7 to 14. We are going to select sweep results, go into Excel. You can close this one, back to input menu. This is the Excel file for this simulation. And we are going to copy. Okay, this is not right. Let's see. Oh, wait. Okay, this is right. We're going to copy this one. Select, copy this, and go back to our chemical precipitation data file. I'm going to right click, paste special, or no, you can just directly paste it. Paste. I'm going to insert a line to separate this one. So this is, let me add one more row. So this one is no NTA. This is with NTA, and this is moles per liter. We want in milligrams per liter. You're going to multiply moles per liter into 63,000. That will give you milligrams per liter. Double click here, it will fill automatically. And then copy this one. Go to this plot. Paste special. Paste the link. And this is with NTA. It's just a small difference in the decimal places, but that should be fine. Let me make this bigger. Right click, select data, add with NTA, and you want to add pH in the x-axis. Y-axis will be the dissolved copper. Okay. And let's add one more thing. Double click on the chart. Add chart element, legend. I want the legend on the top. So we have the no NTA with NTA. I want to make one minor change here. Double click on this one and go to text options, axis option. I want to change this to 10. So essentially we are zooming in to see this one. What you can see is when there is no NTA, you see that copper, dissolved copper is less than 1 in the pH range of about 7.5 to 12, and then again it goes back up. Whereas in the presence of NTA, the lowest we can get is about 6.3. Our treatment goal is to get less than 1. So what happens is, when NTA is present, NTA combines with copper and does not allow copper to form copper hydroxide precipitate, which is what we defined in the speciation model. So now if you want to remove copper as a copper hydroxide, we need to break copper NTA complex. To do that, you can add calcium, which will compete with NTA and free copper, which can form copper hydroxide when the pH increases. The model assumes that when copper hydroxide is formed, it is removed from the water. So the dissolved copper is removed as copper hydroxide precipitate. So let's go to, I'm going to save this one. So we did step 9. Now step 20, for the same model, add calcium and then follow step 7 to 18. Let's do that. Now calcium, I'm going to add 0.01 molar now. Drop down menu. Press C, calcium is right there, Ca2 plus. I want to add 0.01. Add to the list. Run vMinteq. Selected speed result. Print to Excel. And if you click here, this is the previous one. So I'm closing it. I already copied, I don't have to save it. So this is the new one with calcium. Let's copy this one. Copy and go to this one. Let's rename this as data sheet. And I'm going to paste it right here. Okay, so this is with NTA plus Ca2 plus equal to 0.1 molar. Okay. Now this is moles per liter. We want to convert this to milligrams per liter times 63,000. Again, double click with this symbol, it fills up. Right click, copy. Right click, paste special, paste as link. So this is with NTA and Ca2 plus 0.1 molar. Now let's make the plot. Select data, add NTA Ca2 plus 0.1 molar. Edit. At the x-axis, starts from 3, goes all the way to 13, and y-axis, we are looking for this one right here. That's it. I'm going to click OK. So this line right here is the same simulation when you add calcium at 0.1 molar. So now calcium combines with NTA and frees up copper. So copper can form copper hydroxide, precipitate, and be removed from water. So if our treatment goal is 1, we are able to achieve less than 1 in the pH range of about 9 to 12. Now the same simulation you can run for a few different copper concentrations. So if you look at the instruction, few different calcium concentrations. I have the calcium concentration 001, 01, 0.1, 0.05, 0.005. So we just ran this simulation. Let's do the other 4. I'm going to go back to input. Calcium, I'm going to change it to 01. Add to list, run vMinteq. Selected speed result, print to Excel. Again, this is the old one. I'm closing it. I don't have to save. I already copied it. This is the new one. I'm going to copy this and paste to my data file. Paste. And so yes, now the calcium concentration 0.01. Let's convert to milligrams per liter. Copy this and paste it here as a link. Now this is the concentration here is 0.01. I'm going to go this right click, select data, add NTA Ca2 plus 0.01 molar. Now X is pH starting with 3 and goes all the way to 13. Y is the most recent simulation result. Okay. Now you can see this line, which is for 0.01 molar calcium. So let's save this one. Close this one and save. Anyway, so I did it for no NTA with NTA 0.1, 0.01 molar. I want you to do for all the 5 different concentrations and make this plot. So this is the plot I want you to draw. It will show you the effect of calcium and the pH range, the x-axis at which dissolved copper is less than 1 milligrams per liter. I also want you to make these two figures. So the way to make those two figures is double click here, minimum, maximum changes to 70. Now it goes all the way to the top. Now I'm going to copy this one, paste, double click here, active option, active option, changes to 10. Okay, essentially you're looking at a zoomed in version of this figure. Okay, now let's close this one, back to input menu. Your instruction, so we did, I wanted to do 5 other, I already showed you how to do 2 different calcium concentrations. So please do try 3 more calcium concentrations. And the last step, instead of NTA, use EDTA and repeat the same simulation. All you have to do is go back here, press E, it brings up all the E here. Click on EDTA, add same concentration as NTA, which is 0.0001, add to the list, click View List, go ahead, remove NTA. So when you're testing for EDTA, you can remove NTA. Again, remove calcium at this point. Now run your simulation with sodium, nitrate, copper, NTA, and make this plot. The one with this line, you're going to get with NTA. And same way, add different concentrations of calcium and see how it looks. Is there a difference between NTA and EDTA in terms of copper precipitation in the presence of calcium? So you will make these two figures with NTA. Same way you can make 2 figures with EDTA. Now all the tables are listed here. This file is available for you in Moodle. All these table values, you can fill it up after we do the lab part. So the chemical precipitation lab is two components. One is the model simulation. We'll run the model simulation, get this figure, test it out in the lab, see how well the model simulation matches with our lab experience. So you can try this one ahead of time before coming to class. That way it will be easy for you to better understand what happens when you do it in the lab.